The strangest part of science isn't what we know, it's what we still don't. Even with AI models predicting protein folding and telescopes spotting galaxies from the dawn of time, some puzzles resist every explanation. Why do our brains sync up with contagious yawns? Why isn't everyone born right-handed? And why does the ground sometimes tear itself open as if Earth is playing with explosives? In this video, we'll run through 20 of science's biggest open questions, what's understood so far, what remains missing, and nailed newest clues. Some are climate bombs under the Arctic, others are radio pings from galaxies away, so let's begin beneath our feet. Exploding Siberian craters, Earth's Arctic time bombs. Picture a frozen wilderness where the Earth itself suddenly ruptures, leaving behind a raw opening so deep it looks like the land has been hollowed out by an underground blast. This is not a fiction scene. It has been unfolding across Siberia, where enormous craters have appeared in the tundra as if the ground were tearing apart from within. Local reports describe strange bulges forming in the soil before bursting outward with violent force, scattering frozen debris across the landscape. During the very first documented case in 2014, witnesses even claimed flames shot several meters into the air, an extraordinary but rare detail to how explosive these eruptions can be. Investigations point beneath the permafrost for answers. The leading hypothesis centers on methane hydrates, fragile ice-like crystals that lock away natural gas as long as they remain frozen. When warming temperatures destabilize these pockets, methane gas builds until the pressure overwhelms the ground above. Once the surface gives way, the release is explosive enough to fling soil, rock, and ice outward, leaving behind a crater up to 90 meters wide or 70 meters deep. Those who have experienced the blast firsthand describe earth-shaking booms echoing through the tundra, a sound more like artillery than natural geology. In recent years, the scale of the problem has grown clearer. Satellite surveys have identified thousands of potentially unstable mountains across northern Siberia, with earlier analyses flagging around 7,000 as features of concern. Each one may be a site where gas is building below ground, raising the possibility of sudden collapse. Scientists had long suspected dozens of such risk zones might exist. Finding thousands revealed that this is not an isolated curiosity, but a broad and still unfolding threat. Even so, the story is not settled. Methane hydrates remain the most widely supported explanation, but other mechanisms are still on the table. One competing idea is that microbes waking up as the permafrost thaws are generating fresh methane right within the active layer. Another alternative points to pressurized carbon dioxide rather than methane as the driver of the explosions. The shortage of direct samples from beneath these unstable features makes the mystery more difficult and more dangerous to resolve. Scientists disagree on the details because safe sampling opportunities are so rare. The unpredictability of the craters only deepens the concern. While some collapse into modest holes, others carve colossal pits large enough to swallow lakes. Field teams in recent years have reported unstable domes that later ruptured into fresh craters, sometimes at sites they had just retreated from. With every eruption, high concentrations of methane are released, about 80 times more potent than carbon dioxide at trapping heat in the short term, strengthening the cycle of thaw, release, and further warming. Researchers can say with confidence that more craters are likely ahead, but not where or when. And satellites now show thousands of suspect hills. But we still can't say how many are true ticking time bombs. Next, we'll look at another planet-sized hole, this time in the gravity field. The Indian Ocean gravity hole, the place where Earth is lighter. In the middle of the Indian Ocean lies a gravitational oddity so striking that scientists gave it a proper name, the Indian Ocean Geoid Low, or IOGL. Spanning close to 3 million square kilometers southwest of Sri Lanka, it marks the deepest depression in Earth's geoid, the mathematical model of sea level shaped by gravity and rotation. Here, the ocean's surface dips by as much as 106 meters relative to the global average, as if the planet's gravitational fabric has sagged. Sailors crossing this patch won't float differently and no compass spins out of control. The variations are invisible to the human body. Only precise satellite measurements, sensitive enough to catch minute orbital shifts, and deep ocean pressure sensors show how distinctly weaker the pull is here compared to elsewhere. By the scale of geophysics, though, that makes this more than a passing anomaly. It is the planet's most pronounced gravity low. Under normal circumstances, gravity behaves. Predictably, dense material underground strengthens the pull. Lighter rock or thinner crust softens it. Mountains register as slight highs while deep basins record dips. What makes the IOGL remarkable is that it sinks far deeper than any hollow ocean basin or crustal thinning can explain. In this region, Earth behaves as if a vast section of its usual weight is missing. The origins of that missing weight have been debated since the anomaly was first charted in 1948. One line of thought argued for a sunken slab of long-lost seafloor from the vanished Tethys Ocean, lodged deep in the mantle. Another suggested rising plumes of lighter, hotter rock might have spread onto the Indian Ocean and reduced the density below. Still others pointed toward complex interactions between Earth's deep manostructures and its outer layers, with currents of rock circulating on immense scales that suddenly warped the surface above. Recent studies have brought these ideas together into sharper focus. Geodynamic models published over the past few years suggest that the IOGL stems from low-density mantle material well below Earth's crust, connected to shifts in an enormous upwelling beneath Africa known as the superplume. According to simulations, fragments of oceanic crust that subducted millions of years ago may have redirected the plume's heat eastward, feeding lighter material into the region beneath the Indian Ocean. This would account for the dip in the geoid without requiring a single dramatic culprit. Researchers emphasize, however, that the exact configuration is still debated. The anomaly is explained in broad strokes, not yet in detail. To refine those strokes, scientists have deployed ocean floor seismometers and run numerical models that simulate hundreds of millions of years of mantle movement. These efforts show that IOGL is not just a curiosity on a map, but an active target of investigation. In other words, it's a mystery with a roadmap, not a rumor. What makes this more intriguing is how ordinary the surface seems. The sea looks flat, divers feel no difference, equipment runs normally. Yet beneath that calm ocean lies a gravitational hollow, spanning millions of square kilometers, created by processes far deeper than we can see. Other gravity depressions exist, such as one in Canada linked to the melting of ancient glaciers, but none arrive at the Indian Ocean scale. The IOGL reminds us that Earth's interior reshapes the surface in invisible ways. And just as these hidden forces alter how we picture the planet itself, new evidence is also reshaping how we picture the creatures that once ruled it. What dinosaurs really looked like. Think back to the dinosaurs you first learned about. Massive, lumbering reptiles with rough scales, colored in dull greens or browns. That image is deeply familiar, but fossils suggest it was never the full story. Evidence from preserved feather imprints and skin impressions shows that many species carry coverings very different from the old reptilian stereotype. Thin filaments, quills, and in some cases full plumage appear in the fossil record, pointing toward a far more varied look. These weren't just simple coatings either. Their structure hints that distinct colors and patterns were widespread among dinosaurs. The most important clues come from melanosomes, the tiny pigment-holding organelles found in feathers and skin. Paleontologists study their shapes because they correspond to specific colors in modern birds. Multiple studies have recovered fossilized melanosome arrangements consistent with not only brown and black pigments but iridescent shimmering hues as well. This means at least some dinosaurs may have flashed colors like peacocks or hummingbirds, a striking departure from the gray and green predators painted in older textbooks. That realization forces a rethink of how these ecosystems looked and behaved. A world once imagined in earthy muted tones may instead have been full bright contrast, where visual display played a major role. If predators and prey carry distinctive colors, then recognition, intimidation, and mating displays all become more plausible as important parts of their biology. This adds a new dimension to how scientists reconstruct dinosaur behavior, and it continues to fuel debate as more fossils preserve details of their outer coverings. One of the most challenging reconstructions concerns Spinosaurus. Its long jaws and crocodile-like teeth indicate an aquatic diet, and its bone density suggests strong swimming ability, supporting the semi-aquatic interpretation. But whether it spent most of its time in the water or still hunted extensively on land remains debated. Then there's the signature cell on its back. Paleontologists have proposed uses ranging from visual display to heat regulation to stability when moving through water. No single function has been universally accepted, leaving its purpose an open question. What is clear is that Spinosaurus was far stranger than the bulky, swamp-dwelling animal drawn in earlier decades. Other recent finds add even more vibrancy to the picture. Some fossils preserve pigment-bearing structures or chemical signatures that strengthen the case for complex coloration. These specimens suggest hues beyond earthy browns, patterns and shades that would have made many dinosaurs far flashier than once believed. So what about the infamous Velociraptor of blockbuster fame? Its closest reconstructions today look much less like miniature tyrannosaurs and far more like lean bird-like predators cloaked in feathers. If you picture one now, think less scaly T-Rex and more pissed-off hawk. The murder chicken comparison isn't far off. These updates mean museum models, toys, and school posters are already outdated, as paleontology continues to replace the uniform drabness of old depictions with a vibrant and evolving portrait. And just when you adjust to that new image, science throws another curveball. Not with bones or feathers this time, but with a strange, vanishing substance that keeps appearing on the ground. Star jelly. Goo from where exactly? Imagine crossing a meadow after a stormy night and noticing strange, gelatinous clumps scattered across the grass. Pale, slimy patches that glisten for a few hours before shrinking away and disappearing by the next day. For centuries, people thought this substance came directly from the skies, shaking loose during meteor showers. That story gave rise to its enduring name, star jelly. But investigators now know the meteor link is misleading. Fragile organic gel would burn up during atmospheric entry, so the cosmic connection doesn't hold. The first obstacle is catching it at all. Star jelly rarely sticks around long enough for careful study. By the time researchers arrive, the blobs are often half dissolved, leaving only a thin residue. When preserved, the material turns out to be far less otherworldly than legend suggests, yet that doesn't mean there's a single neat answer. Some collected samples test as frogs spawn with the eggs removed, possibly left behind when predators consume the developing embryos. In other cases, tissue fragments from amphibians or reproductive organs seem to match. Still other instances point instead to molds, bacteria, or slime-like fungal colonies that form translucent mats in damp fields. None of these explanations fits every appearance, and the variability is part of why the mystery keeps returning. When scientists have managed to sample these outbreaks, the results vary considerably. Some indeed hold amphibian DNA, while others align with microbial growths or even industrial byproducts. Historical reports even describe cases where chemical residues, such as battery-cleaning compounds, produced gelatinous patches that look indistinguishable from the folkloric slime. This makes it clear that star jelly is likely a general label we attach to several different processes, not one singular phenomenon. Solving individual cases requires rapid response and sometimes DNA analysis, which explains why so many reports remain unresolved. The blobs vanish too fast. By the time tests are done, the evidence has broken down into unrecognizable mush. This fleeting quality helps maintain the myth surrounding them. Something that looks strange, appears overnight, and evaporates before a clear answer emerges is exactly the sort of event that invites speculation. One striking example came from Britain in 2024, when residents found translucent jelly clumps in fields after a night marked by unusual aerial displays. Samples collected quickly revealed amphibian traces, seemingly closing the case. Yet chemical markers within the same material didn't fully match ordinary frog tissue, sparking new questions about whether different decay processes or environmental factors might complicate results. That uncertainty captures why star jelly retains its allure. It resists easy categorization. The phenomenon survives in folklore because it feels uncanny, material appearing without warning, linked in memory to lights in the sky, and then dissolving before its origin can be nailed down. The truth is that star jelly is a cluster of unrelated events with biological, ecological, and sometimes chemical roots. But the impression it leaves, that nature occasionally produces baffling lights, shapes, and substances we can't quite predict, sets the stage for another riddle of the atmosphere, one that comes not as slime on the grass, but as fire appearing inside storms. Ball lightning, the ghost fire of thunderstorms. During thunderstorms, lightning usually comes as sudden flashes that disappear instantly. But scatter reports describe something far less ordinary, glowing spheres of light that drift, hover, or even roll along the ground, holding their shape for seconds, or in rare accounts, minutes. These orbs, known as ball lightning, are said to float through open windows, glow silently across rooms, vanish without leaving a trace. That persistence is what sets it apart from ordinary flashes and gives ball lightning its reputation as one of the strangest and least understood atmospheric events. Unlike a jagged bolt that lasts just fractions of a second, ball lightning lingers. During World War II, Pilots and crew described glowing spheres entering cockpits and cabins, hanging near equipment before fading away unharmed. These encounters were more unsettling than dangerous, but they raised the same unsettling question. How could lightning behave like a wandering light instead of a violent discharge? Even today, witness accounts describe glowing balls appearing inside kitchens, barns, or hallways, settings that don't match up with existing theories tied to outdoor air discharges. Scientists have proposed several leading explanations, though none can fully account for every report. The main hypotheses are vaporized silicon dust created when lightning strikes soil, producing glowing particles, trapped microwaves forming plasma bubbles that create self-contained spheres, and the formation of small-scale dusty plasmas that can float briefly before dispersing. More speculative ideas exist, but they lack solid experimental or observational support. What complicates matters is that each model can explain parts of the puzzle, but not the wide range of environments and durations reported. Experimental work has produced some progress. In controlled plasma chambers, researchers have generated glowing orbs that mimic certain aspects of ball lightning. In one approach, vaporized silicon particles formed luminous spheres that persisted briefly before dissipating. These lasted only fractions of a second, far shorter than some field reports claim, but they showed that natural soil vaporization could produce phenomena resembling the descriptions. Rarely, spectroscopic captures from actual storm events have been collected, providing chemical fingerprints that hint at plasma processes. Yet these glimpses remain scarce, and no single model has yet captured the full diversity of what witnesses describe. Part of the difficulty in solving the mystery is simply getting good data. Despite a world blanketed in cameras and smartphones, convincing high-quality recordings of ball lightning are still extremely rare. Most sightings occur under chaotic conditions, during intense storms, often without the time or means to capture reliable evidence. This lack of consistent footage keeps laboratory studies and isolated field measurements as the primary sources of clues. In 2023, villagers in China recorded luminous orbs drifting near the ground during a storm, lasting several seconds before vanishing. The video looked strikingly similar to decades of anecdotal accounts, though it still didn't settle the debate. Were they short-lived plasma bubbles or something else entirely? What those observations highlight is just how elusive the phenomenon remains. Surveys suggest only a small percentage of people will ever witness ball lightning firsthand, which has kept direct evidence limited even in the modern era. Scientists can now recreate short-lived imitations in labs, but the longer-lasting natural versions remain unexplained. And that tension between what's observed in fleeting moments and what science can so far reproduce means ball lightning continues to float on the edge of mystery. But while some mysteries flare and vanish close to home, others arrive from far beyond our planet, carried not by storms, but by signals caught once from deep space. The WOW signal, space's one-off ping. On August 15, 1977, the Big Ear Radio Telescope at Ohio State University recorded something that has puzzled astronomers ever since. While scanning the sky for the SETI project, the instrument picked up a strong, narrow-band signal at 1420 MHz, the emission line of neutral hydrogen, a frequency researchers had long regarded as a natural cosmic reference point and potential hailing channel for interstellar communication. The signal lasted for 72 seconds, rising, peaking, and fading exactly as you would expect if the telescope's beam had swept across its source in the constellation Sagittarius. When astronomer Jerry Emmon reviewed the printout, he circled the anomalous string of numbers and wrote a simple note of surprise. Wow! That single word became its name. What set the detection apart was how sharply focused it looked. Natural emissions from stars, gas, or nebulae usually come spread out across wide ranges of frequencies. The WOW signal was needle-thin with a clean, narrow profile that equipment was specifically tuned to catch if an intelligent transmitter were deliberately broadcasting. Its brief but structured shape matched almost perfectly what SETI scientists had been hoping to find. Yet almost immediately, the mystery ran into a wall. Once the signal faded, it was gone for good. Big Ear scanned the same piece of sky again and again with no result. Other observatories pointed antennas toward the Sagittarius coordinates, including campaigns with more sensitive instruments, but none detected anything similar. Across decades of follow-up work and multiple generations of radio telescopes, the signal has never been recorded again. That persistent silence is why it still sits as one of the most tantalizing, yet inconclusive events in SETI history. Proposed explanations cover a wide range. Some suggested it was Earth's own interference, a stray satellite transmission or military broadcast bouncing back into the dish. Others proposed a natural astrophysical source, such as clouds from comets emitting hydrogen at the right frequency. More speculative voices left open the possibility that it was exactly what many were hoping, an artificial transmission from elsewhere. Each idea runs into problems. Reflections from Earth do not account for the signal's consistency and strength. Cometary hydrogen emissions occur at the right frequency but fail to match the sharp, narrow band profile that Big Ear recorded. No hypothesis has satisfied all the data points. Modern tools have been brought to bear. In 2025, researchers trained machine learning systems on the original data alongside catalogs of satellites, comets, and known celestial emissions from that era. The algorithms ruled out human-made interference and removed several astrophysical candidates. What they did not do was provide a new solution. The analysis only narrowed the field, leaving fewer options without closing the case. That is the unsettled heart of the WOW. Signal. Detected once, never repeated, and unmatched by any known natural process or technology we can confirm, it remains unexplained. Observatories continue to listen toward Sagittarius, still waiting for another signal, but nothing has spoken up since. It's the closest we've come to an unanswered knock at the cosmic door, so why did no one ever answer? Quantum consciousness. Are we all subatomic brains? Your brain contains about 86 billion neurons, firing electrical signals and exchanging chemicals in an intricate pattern that drives perception and thought. But some researchers argue that this circuit-level description is missing something. They propose that consciousness may also depend on quantum effects, the same phenomena that govern subatomic particles. This idea, sometimes called quantum consciousness, is one of the most controversial intersections of neuroscience and physics. The best-known version of this theory was developed by physicist Roger Penrose and anesthesiologist Stuart Hameroff, who suggested that networks of structures inside neurons, called microtubules, could host quantum processes. According to their orchestra model, superposition and entanglement inside these scaffolds might help generate conscious awareness. If this were true, then thought itself wouldn't just emerge from classical brain circuits. It would arise from quantum mechanics written into our biology. Mainstream neuroscience pushes hard against this view. The brain is warm, wet, and noisy, exactly the kind of environment where quantum states should collapse nearly instantly. Researchers like Christoph Koch at the Allen Institute argue that any coherence would vanish too quickly to influence thought, making the orchestra, our model, highly implausible. From this perspective, consciousness remains fully explainable through biology and network dynamics without invoking fragile physics. Yet there are a few findings that keep the debate alive. Anesthetic experiments using xenon isotopes have raised questions about whether quantum interactions might play a role in how anesthesia suppresses consciousness. The gases behave differently depending on their nuclear spin, hinting, though not proving, that very small-scale quantum effects might influence awareness. In parallel, laboratory experiments have detected surprisingly long-lived quantum coherence in biological molecules, such as proteins and pigments in photosynthetic complexes. These aren't neurons, but they suggest life can occasionally sustain quantum states longer than many scientists once thought possible. Still, the gap from those experiments to actual cognitive process remains huge. No study has demonstrated that neurons directly exploit quantum behavior to produce thought. What has emerged are intriguing hints, reports of ultra-fast, coherent patterns inside neurons lasting trillions of a second, detected in 2025 by 2 independent groups. The results were highly tentative and have not yet been reproduced widely, but they kept the possibility from being dismissed entirely. For now, skepticism remains the dominant stance. Neuroscience can explain perception, memory, and decision-making without quantum add-ons, and many researchers view quantum consciousness as an overreach rather than a necessity. If one day evidence does connect cognition with subatomic uncertainty, the implications for free will and the nature of awareness would be massive, but that is a very big if. Bottom line, quantum consciousness is one of the most provocative ideas at the boundary of physics and neuroscience, plausible enough to test, but far from proven. And if we struggle this much to understand the nature of our own awareness, it raises an even bigger puzzle. What does that say about awareness elsewhere in the universe? The Fermi paradox: where is everybody? The Fermi paradox begins with a question that sounds simple but cuts deep. If there are billions of planets and habitable zones across the galaxy, why haven't we seen solid proof of intelligent life? Modern astronomy has confirmed that Earth-like planets are not rare. Hundreds have already been cataloged, with thousands more candidates. Statistically, the odds should favor not just microbial life, but also technological civilizations are rising across cosmic history. Yet after decades of listening, searching, and scanning for technosignatures, we still have no confirmed signals or artifacts. The silence stands out more the more data we gather. The reasoning works like this: if advanced life emerged even a handful of times, then at least some civilizations should have spread outward, leaving signs that we could detect. These could be consistent radio transmissions, vast engineering works like Dyson swarms, or unfamiliar energy signatures on stars. Intelligent expansion across billions of years ought to leave a cosmic fingerprint. But despite major SETI campaigns, sensitive radio surveys, and repeated checks of anomalous stars, we have not observed anything that qualifies as clear evidence. The paradox sits in that gap between the high probability suggested by numbers and the absence of observational confirmation. A central difficulty is uncertainty. We can estimate star counts and planet populations, but the key variables, how often life arises, how frequently intelligence follows, and how long technological societies persist, remain unknown. Adjust those numbers in different ways, and you either get a galaxy filled with civilizations or a sky where we're likely alone. Both scenarios can flow from the same basic framework, which is why reasonable scientists disagree so strongly on how surprising the silence truly is. To make sense of that silence, 4 classic resolutions are often discussed. Civilizations might be fragile and short-lived, extinguishing themselves through collapse or war. Intelligence might rarely evolve at all, making Earth a statistical outlier. Some societies could choose deliberate quiet, avoiding broadcast to protect themselves. And another possibility is observational. Signals might exist, but they arrive in unfamiliar forms or across channels we are not yet equipped to recognize. Each is only a sketch, but together they mark the range of serious explanations. In 2025, the paradox sharpened with new evidence from exoplanet surveys. Spectra of dozens of atmospheres hinted at chemical patterns linked to biological processes. None suggested intelligence outright, but they emphasized that habitable environments and living chemistry are common. If simple life is widespread, why does the ladder to technology appear so empty? That tension drives the paradox harder with each new catalog update. The longer we listen without hearing anything, the more the silence speaks. The Fermi paradox remains not just a puzzle about probability, but a loud absence in the data. It underscores how much of our universe seems unaccounted for, both in terms of signals from neighbors and, more fundamentally, in the basic matter that holds everything together. Dark matter, missing mass of the universe. 85% of the universe's matter is hidden from view, invisible to any telescope, yet its presence shows up everywhere in the numbers. Astronomers call it dark matter, and by current estimates, it outweighs the familiar matter of stars, gas, planets, and people by more than 5 to 1. That means everything we can see and touch adds up to only a fraction of the cosmos, with the bulk existing as something unknown. The earliest indications emerged while studying galaxies. Decades ago, astronomers saw that stars on the outer edges of spiral galaxies were orbiting much faster than the visible mass could hold together. By classical calculations, those stars should have flown outward into space. Instead, they stayed in neat spirals, as if anchored by an unseen force. The same puzzle appears at larger scales in galaxy clusters. Their member galaxies move so energetically that visible mass alone cannot bind them. Something invisible, yet heavy enough to act as cosmic glue, is at work. Over the years, physicists have offered several candidate particles to explain this discrepancy. Weakly interacting massive particles, or WIMPs, were long favored as a solution, as they could slip through ordinary matter almost undetected while providing the required mass. Axions, far lighter hypothetical particles, offer another option, spreading through space as a subtle background field. Other proposals include sterile neutrinos, faint cosmic cousins of known neutrinos. All these ideas hinge on the possibility that a new particle family still undiscovered is hiding just out of reach of experiments. But despite the range of candidates, no one has detected a single dark matter particle. Underground detectors filled with liquid xenon and other dense materials have monitored for years, designed to catch a rare interaction. Particle accelerators have smashed protons together to recreate high-energy conditions in the hope of seeing new signals. Decades of direct detection experiments, both underground and colliders, have so far returned nothing. Each null result removes swaths of parameter space where dark matter could exist, but none provides a definitive answer. In 2025, China's Panda X experiment reported further exclusions, closing off major mass ranges once thought promising for WIMPs. With each such result, the straightforward possibilities shrink. Either dark matter is stranger than anyone predicted, or the theoretical framework itself is flawed. This is why some researchers now suggest alternatives, such as modifying the laws of gravity rather than invoking unseen matter. Yet those models run into conflicts with another compelling line of evidence: gravitational lensing. Whenever massive clusters bend and warp light from more distant galaxies, the degree of distortion points to far more mass than visible stars and gas can provide. These cosmic mirages make the missing mass extremely difficult to dismiss. In short, gravity insists the mass is there, but telescopes see nothing. That leaves us with two possibilities: an undiscovered family of particles, or a fundamental rewrite of how gravity itself works. Either route would change physics at its base. Dark matter isn't a footnote, it's a cosmic missing person case. And it isn't the only mystery where absence itself tells the story. Sometimes the puzzle isn't about the forces shaping galaxies, it's about the fleeting images our own minds fail to hold on to when we wake up from sleep. Why we forget our dreams. You wake up in the morning, and for a few moments the dream you just had still feels sharp. Scenes linger, voices echo, and it all seems close enough to grab. But by the time you reach the bathroom mirror or make your first cup of coffee, most of it has dissolved. For many people, this fading is so quick that only stray fragments survive. Scientists know the brain does not process dream experiences the same way it handles waking life, and the difference lies in how memory systems work during sleep. The hippocampus, which plays a central role in forming long-term memories while we're awake, operates differently in sleep states. During REM sleep, when vivid dreaming is most common, the usual encoding pathways are less engaged. This means dream events unfold like lived experiences, but the record button isn't pressed as firmly. They're less likely to be stabilized in memory storage, and as a result they vanish quickly when new information floods the mind upon waking. Not everyone experiences this equally. Some people recall long, detailed dream sequences almost every night. Brain imaging research suggests that these high-recall individuals often show more activity in regions like the prefrontal cortex, which is associated with attention and metacognition. This added engagement may tag dream material as more significant, helping those sleepers hang on to narratives rather than isolated fragments. For most of us, however, without that neural tagging, dreams slip away almost as if they were never there. The puzzle grows when you consider how emotionally intense some dreams can be. In ordinary life, powerful emotions usually make memories more durable. Nightmares, for instance, should leave strong traces if emotion alone were enough. Yet even frightening dreams often vanish within minutes. The chemistry of REM sleep helps explain this. Levels of norepinephrine, a neurotransmitter tied to alertness and memory consolidation, run unusually low during REM. Without that chemical boost, even emotional content doesn't get locked into storage. The result? We watch vivid dramas play out nightly, only for the brain to let them disintegrate before morning. There is, however, a way to work with this fragility. Studies show that dream recall can improve if you actively catch the material before it fades. Keeping a notebook or phone by the bed and writing down details immediately upon waking helps preserve the memory trace. Over time, this practice trains the brain to save more content and to hold on to longer narratives. If you want sharper recall, one practical tip is simple: keep a notebook by your bed and jot your dreams the instant your eyes open. So while we understand why dream recall is fragile, different brain engagement, low chemical support, and rapid overriding in the waking mind, we also know it varies person to person and can be shaped by attention and habit. But this gap between perception and outcome isn't unique to dreaming. In fact, the same mind-body disconnect appears in another context, where belief alone can change what we feel, even in the absence of an active chemical cause. The placebo effect. Fake pills with real power. Imagine being handed a pill you know has no active drug inside, and yet your pain eases or your mood genuinely lifts. That odd phenomenon is the placebo effect, one of medicine's most enduring puzzles. Here, fake treatments with no pharmacological ingredients still trigger real, measurable changes in the body. The underlying force is expectation. When a person believes care is being given, the brain can respond by releasing endorphins and dopamine, chemicals that regulate stress, reward, and pain. The relief people feel is not imagined. It registers in brain scans, hormone levels, and reported symptoms. What makes it even stranger is that this effect doesn't always require deception. Emerging clinical research shows that open-label placebos, where patients are told outright that the pill contains no drug, still produce benefits in certain conditions like chronic fatigue and persistent pain. Relief in these trials is not as strong as what comes from targeted medicines, but the repeatability of the result is compelling. That raises wild questions. Could a large part of medicine's power come simply from the ritual of care and the mind's response to it? Researchers have long noted that placebo responses vary dramatically between individuals. Some people report striking improvement, while others feel little to nothing at all. Current evidence points to a mix of influences, psychological factors like expectation and suggestibility, neurochemical systems such as dopamine and opioid pathways, and possibly genetic differences. But while genetics are a focus of study, no single predictive marker has been validated, and no genetic test can currently determine whether someone is a placebo responder. That variability keeps the phenomenon deeply personal and difficult to predict. The debate around what placebos really achieve is ongoing. They do not clear infections, shrink tumors, or replace antibiotics, but they can influence systems that are heavily connected to the brain, like pain perception, stress regulation, and even immune activity. In those areas, belief itself appears able to modulate physiology. This suggests the brain has access to levers inside the body that can adjust symptoms based not on chemistry from outside, but on signals generated by expectation. The placebo effect highlights just how blurred the line is between the psychological and the physical. Real-world trials illustrate this clearly. In one study of patients with chronic back pain, those knowingly taking placebo pills still showed meaningful improvements in discomfort and daily mobility compared to patients who received no intervention. Importantly, no strong side effects occurred, since the capsules contained no drug at all. The routine of treatment, the act of swallowing a pill, the environment of trust with doctors, the belief in doing something constructive, seemed to prompt the nervous system into adjusting its own output. In practice, the placebo effect acts less like a cure-all and more like a subtle but powerful amplifier of the body's existing systems. Doctors continue to explore how to harness it ethically alongside standard medicine, maximizing patient benefit without misleading them. Regardless of whether it brings partial relief or lasting change, the placebo remains a striking reminder that healing is shaped as much by perception and context as by chemistry in the bloodstream. Of course, not every medical mystery is reassuring in its implications. Some shift from curious to unsettling, cases where the body itself seems to ignite, leaving behind scenes that are as disturbing as they are unexplained. Spontaneous human combustion, death by fire without fire. Picture the scene. Investigators enter a room to find a body so extensively burned that only fragments remain, yet the surrounding furniture and flooring show little more than minor scorching. For centuries, such unsettling cases have been recorded under the label of spontaneous human combustion. These reports describe deaths marked by unusually localized damage, intense destruction of human tissue, while nearby material, which should have ignited under ordinary circumstances, often appears oddly preserved. Historical accounts stretch back to at least the 1600s, appearing in coroner's notes, newspaper clippings, and books of curiosities. The pattern is usually the same. A body consumed far beyond what a simple household accident seems able to explain, with limbs or extremities sometimes left behind untouched. These unusual details fueled speculation that the fire must have originated within the body itself. Over the centuries, these stories grew into folklore, blurring the line between genuine forensic puzzles and sensationalized accounts. Most scientists and fire investigators adopt a more grounded explanation, pointing to what is often called the wick effect. This proposed mechanism suggests that once clothing ignites from an external spark, a dropped match, an overturned candle, a still-lit cigarette, the fabric can trap melted body fat. The fat then soaks into the clothing like wax in a candle and sustains slow, prolonged burning. In principle, Such smoldering can reduce large portions of a body while leaving the fire surroundings relatively undamaged. Forensic experiments with animal tissue have shown this process can occur under controlled conditions, producing results that echo aspects of the reported cases. However, skepticism arises because not all reports include evidence of a likely ignition source. Some claim no nearby fire was detected, and the level of bone or tissue destruction seemed to advance for the relatively low temperatures that clothed smoldering fires usually reach. The absence of clear scorch patterns on adjacent objects also raises questions, since even a prolonged burn should transfer heat beyond the body itself. These inconsistencies keep the subject alive in public imagination, even as most forensic specialists remain confident in conventional explanations. In recent years, reassessments of older reports have leaned toward natural causes like prolonged, unnoticed burning, accidents involving alcohol or accelerants, or simple misreporting by inexperienced observers centuries ago. While elements of the wick affect may account for parts of the burn pattern, no universally agreed upon explanation covers every sensational claim. For that reason, experts generally suggest treating spontaneous human combustion less as a verified scientific mystery and more as a mixture of rare forensic puzzles and enduring urban legend. It's this blend, cases with a kernel of unexplained detail surrounded by layers of cultural storytelling, that explains why the topic continues to persist. No one has ever documented such an event under controlled observation, and the very term spontaneous combustion remains controversial among scientists. For now, the most grounded view is that these incidents, however strange, can be explained through known fire dynamics in unusual circumstances. Still, stories of unaccountable flames tap into deeper questions about how much we really understand about bodies, signals, and unseen forces. And sometimes, mysteries don't come from destruction at all, but from a sound or vibration so steady and familiar that many of us hear it daily without fully knowing why. Why cats purr more than feline happiness? Most people think a cat's gentle rumble means one thing: bliss. In reality, the picture is more complicated. Cats also purr when they're injured, stressed, frightened, or even giving birth. The behavior appears in contexts that go well beyond comfort, suggesting that purring isn't simply a soundtrack to happiness. Instead, it may serve two overlapping purposes, sending signals to others while offering physiological benefits to the cat itself. What draws the most interest is the frequency of the sound. Recordings show that purrs typically fall between 25 and 150 hertz. Some research indicates that mechanical vibrations in this band can stimulate bone density, tissue repair, and muscle recovery in controlled laboratory settings. That overlap has led scientists to wonder whether cats purr, not only for social reasons, but also as a form of self-healing, gently vibrating their own bodies at therapeutic frequencies. It's an intriguing symmetry. A noise made during stress or injury could double as a recovery tool. This idea gained more traction in veterinary studies published in 2024, which suggested that animals exposed to vibrations within the same range experience faster bone healing. That doesn't make purring a proven treatment, but it nudges the possibility that evolution shaped cats to use these low-frequency rumbles as a built-in repair mechanism. Alongside, it remains an unmistakable communication tool. From their very first days, kittens purr against their mother's body. They begin before their eyes open, using vibrations as a kind of tactile signal to reassure both sides of the bond. Later in life, the same signal may broadcast comfort, need, or even distress to companions, feline or human. This double function makes purring harder to categorize. Is it primarily a call for connection, or is it self-maintenance cleverly disguised as a social cue? Evolution may have favored its persistence because it accommodates both roles. The potential spillover to humans is worth noting. In trials with therapy animals, exposure to cats was linked with lower stress and reduced cortisol levels among anxious participants. Whether the effect comes from companionship itself or whether the purr's frequency layers on extra physiological calm remains uncertain. Either way, therapy cats appear to offer real benefits, and that raises the question of whether humans could someday adapt feline vibrations directly for medicine. Some researchers are already experimenting with machines that mimic purring frequencies. The hope is that low-frequency acoustic therapy might support recovery from bone injuries, reduce inflammation, or simply ease stress without medication. While practical applications remain early, the possibility reinforces how something as ordinary as a household pet may hold unexpected medical potential. In the end, purring seems to be a remarkably efficient design. It tightens social bonds while possibly helping the body repair itself, good communication, and maybe good physiotherapy. No surprise, therapists have long relied on cats' presence in calming spaces, whether for the comfort of the vibe or the science of the vibrations. And yet, not all low, steady sounds are welcome. Some linger as unexplained noise that follows people in their daily lives with no obvious source at all. The Taos hum, a sound only some can hear. In Taos, New Mexico, a number of residents describe a peculiar sound that never stops. Known locally as the hum, it's reported as a low, droning noise, often compared to far-off rumble of engines or a muted electronic buzz. Only a small portion of the population, about 2% by some estimates, can hear it. But for those who do, the experience can be deeply disruptive. People say it interferes with sleep, makes concentration difficult, and sometimes leads them to seek medical help when it refuses to fade. Acoustic specialists have tried to measure what these residents describe. The frequencies most often reported cluster near 30 Hz, right on the border of human hearing. Below that lies infrasound, vibrations that most people cannot perceive consciously. This would fit with the unusual fact that some Taos locals hear it while their neighbors remain in silence. Instruments have confirmed faint low-frequency vibrations in the region, but results vary. One test may detect a tone-like hum, while the next records almost nothing. Extensive monitoring campaigns have captured infrasound, but no consistent repeatable signal explains what the residents report. The mystery has not remained within the New Mexico desert. Similar complaints have surfaced in Bristol in the UK, in Windsor in Ontario, and in scattered communities elsewhere. Each location shares the same perplexing details. Only a fraction of people notice the noise, and when scientists bring sensitive microphones, the recordings don't always match what listeners describe. That mismatch makes it difficult to pin the cause on a single source. At best, microphones capture background vibrations from industry, infrastructure, or weather systems, but not at levels that account for the selective perception of only a few residents. Over the years, two broad classes of explanations have taken shape. On one side are environmental causes, industrial equipment humming at long distances, geological tremors, or atmospheric interactions producing low-frequency sound. On the other side are personal auditory phenomena, tinnitus or subclinical auditory sensitivity that causes individuals to perceive vibrations others cannot. Both avenues have been investigated. Environmental monitoring shows real low-frequency noise exists, while medical evaluations highlight ear function and neurological differences. Yet neither path has provided a final answer, since neither can account for every case that has been reported. For some, the discomfort becomes so severe that they move away in search of silence. Disturbingly, a subset of sufferers claim the sound follows into new homes, suggesting an internal origin rather than an external one. Others insist the hum is tied to specific valleys or towns, pointing back to environmental sources still not identified. The divide between those who swear it is real and those who never hear anything keeps the debate alive. What researchers can agree on is that the phenomenon only affects a small percentage of people. Those reports are genuine in their impact, and no single explanation has been proven. For the residents lying awake at night, the hum is a steady, unwanted soundtrack without a clear source. And mysteries like this one, where perception doesn't line up neatly with the measurements, echo another puzzle of the mind. Not about what we hear, but about what we feel we've lived before. Deja vu, brain's replay trick. Deja vu is one of those familiar brain tricks nearly everyone encounters at some point. You walk into a new place, hear a conversation you're certain is happening for the first time, and then suddenly it feels uncannily familiar, as if you've already lived it. The sensation is brief, but strong enough to convince the mind that reality is looping. That eerie flash of recognition when you know intellectually it can't be true is why deja vu is often described as the brain's replay glitch. Neurological studies suggest the effect comes down to how memory circuits sometimes slip. There are two leading possibilities. One option is an encoding error. The brain takes in new information but mistakenly tags it as a stored memory, generating a false sense of recognition. The second is a timing error. Sensory signals processed along different neural pathways may arrive fractionally out of sync. By the time the delayed signal hits, the brain interprets it as a repeat of what it already experienced a millisecond before. In both cases, the machinery that handles recognition mislabels the present moment as something recalled, producing the haunting impression of familiarity without cause. A strong clue comes from clinical settings. People with temporal lobe epilepsy often report déjà vu at the start of seizures, sometimes so intensely that it overwhelms the ordinary version healthy individuals experience. That link suggests irregular bursts of electrical activity in the brain's temporal lobes regions. Critical for memory and recognition can trigger the sensation. Supporting this, neurosurgeons performing operations have sometimes induced déjà vu deliberately by stimulating parts of the hippocampus or surrounding cortex. Patients consistently describe the sudden, compelling feeling of familiarity, even in sterile operating rooms with nothing recognizable in sight. Recent scanning studies have begun to capture hints of this in action. During episodes of déjà vu, activation patterns in the hippocampus can mimic those seen during real memory retrieval. In other words, the brain genuinely behaves as though it's pulling something from storage when, in fact, no matching experience exists. That could explain why déjà vu feels so real. The brain isn't just imagining familiarity, it's running the same circuitry it would use when recalling an actual past event. The remaining puzzle is why it occurs so often in people without epilepsy or brain injury. Current evidence suggests that brief, harmless misfirings in healthy temporal memory circuits are enough to trigger it, though the exact threshold or cause remains unclear. For now, it's classified as a benign slip in brain function. Common, usually fleeting, and without known danger. But that doesn't make it any less unsettling in the moment. In short, your brain sometimes presses the replay button on the present, and that's déjà vu. It's a reminder that even ordinary experiences can feel otherworldly when perception and memory cross wires. And as strange as that is, it pairs with another curious behavior the brain produces, this time not in silence, but with a sound that tends to spread from person to person almost instantly. Yawning, contagious without reason. Yawning presents another everyday behavior that remains strangely unresolved. You've probably seen it happen. One person yawns in a room, and suddenly others follow within seconds, jaws stretching wide almost involuntarily. It seems trivial, yet the fact that it spreads so easily raises a larger puzzle. Why do humans yawn, and why does it replicate across groups with such reliability? Two leading ideas guide current research. One is physiological. Yawning may help regulate brain temperature. By drawing a deep breath and stretching facial muscles, cooler air passes across the head's blood vessels, possibly giving the brain a quick thermal reset. The other idea is social. Contagious yawning often tracks with empathy and social awareness. People who score higher on empathy tests report catching yawns more frequently, while young children who haven't yet developed full social cognition rarely mimic yawns until later in development. Taken together, these perspectives suggest yawning might serve both a self-regulating purpose and a group-coordinating signal. Why both? We don't know. This is precisely what keeps yawning quietly weird. You can even test the question at home. Watch a few clips of someone yawning or sit across from a friend and mimic the gesture intentionally. Some people will find themselves yawning almost instantly, while others remain unaffected. This small experiment reflects what researchers find in laboratories. Yawning spread is consistent but not universal. No study has yet explained why certain individuals resist the effect while others fall into it almost immediately. Attempts to measure the social dimensions have added nuance rather than closure. Contagious yawning seems less tied to tiredness itself and more aligned with subtle bonding behaviors. It may once have helped groups align rest and activity cycles or served as a silent signal of readiness. Yet at the same time, its inefficiency is striking. Evolution produces more reliable ways to coordinate behavior than having everyone stop to yawn together. That mismatch between how common yawning is and how vague its function remains is part of the mystery. Researchers also point out the unpredictable nature of triggers. Videos filled with yawns don't compel everyone watching. Some participants never respond despite repeated attempts. Others find it irresistible, even struggling to resist in experimental trials. This inconsistency complicates both the cooling and empathy models. If yawning were only about brain maintenance, why would the sight of another's yawn matter? If it were only about social connection, why do solitary yawns still happen so often? Even the act of reading or hearing someone describe yawns can be enough to trigger the urge. Chances are you felt one rising while listening to this explanation. That reflexive tug highlights how strange it is that this behavior has persisted across time, cultures, and species without a definitive purpose nailed down. And while yawning reveals how fragile the boundary between physiology and social connection can be, the next mystery pushes even deeper. It's not about a reflex or a pattern of behavior, but about the inescapable question of inner awareness itself, why there is any conscious experience at all. The hard problem of consciousness. Consciousness is often described as the most personal fact of existence, and at the same time, one of science's hardest open questions. The problem isn't mapping patterns of brain activity that correspond to thoughts, emotions, or attention. Those are what researchers call the easy problems, because they deal with observable correlations. The real difficulty is explaining why those processes feel like anything from the inside. Why does red look like red to you, instead of being processed invisibly with no sense attached? That gap between physical description and subjective feeling is what philosophers call the hard problem of consciousness. Qualia, the raw sensation of experience, are what make the problem so stubborn. A brain scan can show which circuits activate when someone sees a color or makes a decision, but the subjective aspect, the what it's like, refuses to appear on the screen. Neuroscience can describe neural correlates of consciousness with increasing precision, yet the explanatory gap remains. Why should complex signaling in cells produce an inner world at all? No experiment so far has moved beyond correlation to causal explanation. Several frameworks attempt to close this gap. One of the best known is integrated information theory, which proposes that consciousness depends on how much information a system integrates across its parts. In this model, systems with greater interconnected complexity would be more conscious. Another major contender, the global workspace theory, suggests consciousness arises when information is broadcast widely across the brain, making it accessible to decision-making, memory, and language. Both theories offer valuable clues, but each is contested, debated, and incomplete. No consensus unites the field because each leaves unanswered why subjective perspective emerges at all. This divide has encouraged two very different ways of framing the mystery. Some argue it is emergent, an outcome of vast complexity, no different in principle from life itself appearing from chemistry. Others take a more radical stance, that consciousness may be a fundamental property of the universe, woven into the fabric of reality like space-time or mass. If that were true, then self-awareness might exist on a deeper level than neural computation, with implications far outside biology. Both positions capture imaginations, but neither has the evidence to decisively win. The debate doesn't stop with humans. As artificial intelligence produces systems that mimic learning, language, and memory, the question of machine awareness grows sharper. If a network performs like a mind, does it feel like a mind? We have no tool to measure qualia externally, so the question cannot yet be tested. The challenge highlights the same blind spot faced in neuroscience. Subjective experience remains invisible to instruments. At its core, the hard problem asks why there's an inner life at all, not just mechanical input and output. Science can describe brains in detail, but the spark of awareness, the sense of being, remains unexplained. For now, he's left as one of the deepest open riddles, what makes experience possible. And just as we confront mystery within ourselves, telescopes reveal mysteries far outside us. Brief, powerful signals that appear from distant galaxies, lasting only milliseconds and carrying unimaginable energy. Fast radio bursts, millisecond cosmic screams. Radio observatories occasionally intercept radio pulses so quick they register as blips, not waves. These signals are called fast radio bursts, or FRBs. Each one lasts only a few milliseconds, yet most originate far beyond our galaxy, carrying enough energy to be detectable across billions of light years. The first was discovered in 2007, and since then, thousands have been cataloged. Most appear once and never repeat, while a smaller group of repeaters sends pulses multiple times from the same location. The extreme scale is what makes FRBs remarkable. In the instant of a single burst, the radiated energy can rival what our sun produces over several days. To survive the trek across intergalactic space and still arrive strong enough to register on Earth's detectors means the source must be an astrophysical powerhouse. That level of power sits at the edge of what known objects are capable of producing. The most promising natural candidates so far are magnetars, neutron stars with magnetic fields trillions of times stronger than Earth's. They are prone to violent flares that could blast radio energy outward. Other possibilities involve exotic stellar processes, such as plasma clouds twisting emissions or energetic collisions in dense systems. These ideas explain a portion of the population, but not all cases look identical. Some FRBs share features consistent with magnetar outbursts, while others display properties that resist neat classification. In 2020, astronomers managed to tie one FRB to a magnetar within our own galaxy, strongly supporting the connection. Yet in 2025, a repeating burst localized to a dwarf galaxy added fresh complications. The environment there didn't perfectly match predictions for magnetar sources, suggesting more than one type of engine may be at work. Instead of narrowing down the explanation, each careful measurement has tended to expand the list of options. What puzzles researchers further is that a few repeaters show internal structure rather than purely random flashes. One emitted bursts with regular intervals between frequencies, almost resembling coded pulses. The consensus is that extreme astrophysical conditions generate these patterns, but the resemblance to intentional signals is striking enough that the idea of artificial origins tends to resurface. Scientists overwhelmingly favor natural explanations, but the diversity of behaviors makes it difficult to dismiss every other possibility out of hand. Today, magnetars remain the leading explanation for at least some FRBs, while others might arise from different forms of high-energy stellar activity. Still, the population as a whole resists a single unifying answer. What is clear is that these outbursts represent some of the brightest, most energetic events we know, brief millisecond flashes carrying the weight of suns. They're either extreme astrophysics or, if one prefers a dramatic scenario, extraterrestrial beacons. Most researchers bet on physics, but the signals continue to throw curveballs. The fact that these bursts vary so wildly hints at complexity hidden in plain sight. Sometimes that same question of persistence and rarity appears much closer to home, in a human trait that consistently defies easy evolutionary reasoning. Why left-handed people exist. Roughly 1 in 10 people worldwide is left-handed, but why that proportion remains steady has long puzzled scientists. Evolutionary pressures often favor traits that make survival easier, especially when everyday tools, weapons, and cultural systems are built for the majority. If left-handedness carried only drawbacks, it might be expected to fade over generations. Instead, it has persisted across time and geography, suggesting there are balancing factors at work that keep the numbers consistent. One explanation comes from contexts of conflict and competition. Being in the minority can provide an advantage when unpredictability matters. If most individuals train primarily against right-handed opponents, encountering a left-handed rival comes as a surprise. Sports have become a modern testing ground for this idea. In disciplines like fencing, boxing, and mixed martial arts, studies have repeatedly found that left-handed athletes are overrepresented among top performers compared to their share of the general population. The slight edge conferred by rarity could help explain why left-handedness maintained a foothold throughout human history, where fighting skill often impacted survival. Genetics offers another perspective. Research shows handedness isn't controlled by a single dominant gene but by a polygenic architecture, with dozens of genetic variants, each contributing a small effect. This makes handedness more of a probabilistic outcome than a fixed inheritance pattern. Even within families, left-handedness doesn't pass along predictably. The diffuse genetic basis helps explain why humanity consistently produces a minority of left-handers without drifting toward disappearance or dominance. Adding to the puzzle, imaging studies have revealed neurological differences tied to handedness. Left-handed individuals often show subtle variations in brain lateralization, the division of functions across hemispheres. Some findings link these patterns to language processing or problem-solving styles, though not in ways that lend themselves to easy stereotypes. The picture that emerges is that handedness reflects not just motor preference, but broader differences in neural organization, differences that may carry occasional advantages in creativity, communication, or adaptive thinking, even if they appear only in subsets of people. Evolutionary models such as frequency-dependent selection help make sense of the population balance. This principle holds that a trait's survival can depend on how common it is. When left-handers are rare, the surprise factor in fights or competitive encounters boosts their advantage. But if the proportion were to rise too high, that edge would fade, and the balance would return to equilibrium. Such a dynamic could explain why left-handedness remains consistently close to 10% around the world, a balance point sustained by social interaction and competition itself. Cultural pressures complicate the story further. Left-handers have long been forced to adapt to tools, systems of writing, and daily life designed with right-handed norms in mind. Despite this persistent challenge, the trait endures further evidence that biology and social experience intertwine to shape its persistence. Handedness, then, is not a mystery to be solved by one explanation, but the product of genetics, evolutionary dynamics, and cultural adaptation. It reminds us that even a basic human behavior can resist simple answers and settle into a lasting balance. And if the persistence of handedness raises questions about adaptation, another universal human trait does the same on a daily cycle, one where the stakes are not about which hand we favor, but about why everybody insists on spending long stretches of time unconscious. The mystery of sleep. Why be unconscious daily? Every animal with a nervous system, from humans to insects, spends part of its life asleep or in a comparable rest state. The striking feature is how risky this behavior is. Lying motionless for long hours invites predators, reduces time spent feeding, and leaves an organism vulnerable. Yet evolution never removed it. If natural selection had a more efficient solution, we might expect sleep to have been replaced. Instead, it is universal. That persistence means sleep fills a role so crucial that no lineage could abandon it. Current evidence highlights several key functions. Sleep supports memory consolidation, allowing experiences and skills from the day to be stored more effectively. At the same time, the brain's glymphatic system becomes more active, flushing out waste products that accumulate during waking hours. Proteins such as beta amyloid, thought to play a role in neurodegenerative disease, clear far more efficiently during sleep than during wakefulness. These processes suggest sleep provides both cognitive sharpening and long-term protection for neural health. They are not optional upkeep. They are biological maintenance tasks that cannot occur as effectively while awake. This makes the paradox sharper. Why must the brain fully suspend awareness to perform this maintenance? Couldn't it operate in a slower, alert state while still handling cleanup and memory work? The evidence says no. Studies consistently show that only during unconsciousness do these processes function properly. That has led researchers to believe the brain requires an uninterrupted offline state to reset itself at the next period of waking activity. The effects of deprivation reveal how high the stakes are. Animals deprived of sleep decline quickly, far more dramatically than when food is withheld for short periods. In experiments, sleep-deprived subjects can suffer cognitive collapse, immune dysfunction, and in some extreme cases, lethal breakdown. This doesn't prove sleep is categorically more important than food, but it shows that a lack of sleep produces acute physiological damage faster than expected if it were a minor accessory to life. In practice, it functions as a need the body enforces at all costs. This non-negotiable quality emerges in microsleeps. Shift workers, overextended drivers, or soldiers pushed beyond their limits experience brief episodes where their brains involuntarily shut down into fragments of sleep, even as they try to stay awake. No amount of willpower prevents it, underscoring that the system insists on restoration. Laboratory interventions back this up further. Experiments where REM phases were disrupted produced animals with severe learning and memory problems. Skills once practiced disappeared. Without REM, their capacity for adaptation faltered, revealing how central even one part of the cycle is to cognitive function. Yet the deeper question remains wide open. We can see sleep's functions in memory and metabolic maintenance, but why they require nightly unconsciousness remains unanswered. Why does the brain have to shift into blackout mode at all, instead of fine-tuning itself while still awake? We still don't know. One takeaway is clear enough. Protecting sleep isn't optional. Evolution locked it in as mandatory. And that insistence, echoed across insects, birds, mammals, and humans, belongs alongside the many other mysteries that keep showing how the natural world resists simple explanation. From Siberia's exploding craters to the hidden mass of galaxies, this journey has shown how much about our world and universe remains unsettled. These mysteries span a broad range: slime mistaken for stardust, low rumbles in small towns, sudden cosmic flashes, but they all point to the same truth. Even with enormous scientific progress, many questions resist closure. Some puzzles are being chased right now by research teams across the world. Progress tends to arrive in fits and starts, sometimes dramatic, sometimes incremental, so the best approach is to stay curious and keep watch for the next clue. Which mystery surprised you most? Drop it in the comments and I'll pin the most popular pick. If you love the unknown, this channel is where we keep asking the hard questions.